Welcome everybody to this first video of our Calculus 1 course. I'm Alain Léger. I'm going to be your teacher for this course, and we're going to begin today with an introduction to the very first concept of calculus known as limits. So, limits. What is a limit? I think every single concept like this should begin with a clear definition. So we're going to try to give a definition as informal as it may be of what a limit is. So what is a limit? The limit L, big L, of a function f of x as x approaches a value of a. The limit L of a function f of x as x approaches a is a y value being approached. Here's that word again that's kind of like really not so mathematical. That's an O, that's an A, as being approached by the function, by f of x, as x approaches the value A. So what is the limit? It's a y value. The limit is a y value. A value that is actually being approached. So you're approaching a y value when you take a limit. And you approach this y value when x itself, so you see the connection, x and f of x, when x approaches a certain value called a. Now, I understand that this may not be a very satisfactory definition because, hey, what does that mean? That something approaches something else. I'm going to give you a couple of examples in a minute, but it is a concept that is a little bit unsettling. But before that, let's take a look at some notation. We are going to write what we just did over there. We're going to write this as such. So, lim as x arrow a. This will mean clearly x approaches a. So the arrow means x approaches a. The limit of what? Well, the limit of a function. And what is that limit of the function? It's the y value being approached, and we call it big L. Okay, good. So why the concept of limit? Because it is radically different from the concept of an ordinary function. Remark, very important remark. X approaches a means x gets close to a. That's an O. It gets close to a, but it does not equal a. X is not equal to a. So that's the difference between plugging something into a function and evaluating a limit. Plugging something into a function, if you want to know what f of a is, you replace x by a, bonsoir, that's it. But if you want to find the limit, you got to be careful because it means get close to a, approach a. Now, what does that mean? We shall explore some more. So before I erase, I'm going to give you a couple of seconds to put it on pause and finish copying whatever you already don't have copied. And it's a very, very small whiteboard, so we're going to have to erase many, many times. So we're good? Moving on. Okay. So what does that mean? X approaches a. Let us spend a little moment investigating what it means that x approaches a. So x approaches 1, for example, means x is close to 1. But what does it mean that x is close to 1? Well, for example, can you think of a number that is close to 1? I'm sure you can. For example, x equals to 0.9 is close to 1. Or x is equal to 0.99, that is even closer to 1. Or x is equal to 0.999. Okay, you get the picture. So etc. means more and more and more. But should x actually be only less than 1? Why can't it be greater than 1? Tell me, 1.1, is that number close to 1? Well, it certainly is. So is 1.01. It is even closer to 1, isn't it? Or maybe 1.001. And we could actually get closer by adding more zeros between the ones, and we would get a number that is actually even closer to 1. This sort of little example suggests that we can approach 1 either from the left or from the right. So notation, some more notation. X approaching 1 with a little plus in the place of the exponent. Shall means x is greater than 1, right? But always keep in mind that getting close to 1 means we are not equal to 1. So getting close to means I am not exactly there quite yet. X approaching 1 with a little minus in the place of the exponent shall mean that x is less than 1, and also x is not equal to 1. So it's understood when we put the arrow here and we say approach 1, it's understood that either way we are not equal to the value. We are simply getting close to that value. Let me give you an example. Evaluate the limit as x approaches, let's keep it easy, x approaches 1, of a function, let's call it x squared plus x. So the limit is x approaches 1 of x squared plus x. So this is my function right here. This is my f of x right there. And I am trying to find what y value does this function approach when x approaches 1. This is an x value. So there is a connection here between x and f of x. Now, how shall we do that? Let's say at a very intuitive level, we could actually just plug in some numbers. And as long as we don't plug in x is equal to 1 per se, then we're respecting our definition. So let us say x is equal to, okay, I want to be close to 1. Why don't I take that number 0.9? All right. This means that f of x is equal to what? Let's put in 0.9 into that. We're going to get something like 1.71. All right, how did I get 1.71? If you really want to know, do you really want to know? I did 0.9 squared plus 0.9, and I got 1.71. Let's get a little closer to 1 with a value like this, like 0.99. What is f of x when x is equal to 0.99? Well, it is 0.99 squared plus 0.99. Now, what is that going to be equal to? I would say 1.9701. And one last 0.999999. What is f of x? It is 0.999 squared plus 0.999. And what is that equal to? That would be equal to 1.997. 001. Good. Now, what do these values, I'm going to change colors because my blue is dying. What do these values actually mean? Remember what a limit is. A limit is a y value that is being approached when x itself approaches a value. So here, x is clearly approaching 1. Yes? Now ask yourself, f of x is actually approaching what value? From 1.71 to 1.97. From 1.97 to 1.997. What do you think we're getting close to here? We're definitely getting close to f of x is approaching what value? 2. Precisely. So what have we found by doing this? What have we found? We have found that, alors, when I put like 3 little points like this, it means conclusion. So it's the end of the argument. And this argument actually leads me to believe that the limit as x approaches 1 from the left, right, with values that are less than 1, of the function x squared plus x, that y value being approached is actually equal to 2. Ha! Again, quick pause, and you can finish copying whatever you want to copy from this. And then I'll take a look at the values of x from the other side. So let's get rid of this. Don't need that no more. No more, no more, no more, no more. All right, back to blue, baby. So now x is equal to, let me be on the other side of 1. Let me be 1.1. What is f of x if x is 1.1? Well, it's the same function, so 1.1 squared plus 1.1. What is that? That's 1.21 plus 1.1. That's 2.31. All right. Now x is equal to, let's get a little closer. 1.01 is closer to 1 than 1.1. F of x is going to be 1.01 squared plus 1.01. What should that be? 2 point something. 2.0301. You can all do this on your calculator if you want. You can verify that these calculations are correct. Putting in one last value to convince myself that I'm doing the right thing here. So 1.001 squared plus 1.001. That should be pretty close to 2, and it is. So it's 2.00301. So once again, the question we would like to answer. Look at this sequence right here. From 1.1 to 1.01 to 1.001, this sequence is definitely getting close to 1. And in return, this sequence here from 2.3 to 2.03 to 2.003 tells me that this is getting closer to 2.00000 something, which is 2. F of x is approaching 2. The conclusion of this argument, I am pretty sure you can come up with this yourself, is that the limit as x approaches 1 this time from the right side of the function x squared plus x is equal to 2. Lovely. Lovely, lovely. So what do we got here? So let's summarize this example and arrive to some sort of conclusion. So we have found that, well, what have we found? Two things. We have found that the limit as x approaches 1 from the left of the function is 2. We have also found that the limit as x approaches 1 from the right of the function is 2. You will notice that these two numbers are the same. Right? And that is very important for the following statement that we are going to make. This statement concerns exactly approaching a point from the right and from the left. So what can we say from this? It's the same limit on both sides. It's the same limit on both sides. Hence, and we're going to give something a little more formal in a minute, hence, because it's the same limit on both sides, we conclude, hence, for this problem, we are going to conclude that limit as x approaches 1, notice no direction, no minus, no plus, just a 1 of the function f of x, which is x squared plus x in this example. That limit is actually equal to 2. So, again, I'm going to make a quick pause. You can do the same and finish copying what you need to copy before I move on. Quick pause, very quick pause. So, what are we going to say at the end of this thing? We're going to say that that's a very important result. That's a very important result. This result is the following. Limit as x approaches a of f of x exists and equals L only if the limit as x approaches a, I'm going to change colors here for this because it's too important. So the limit as x approaches a from the left of f of x exists and equals L, and if the limit as x approaches a from the right side of f of x also exists and also equals to L. So for a limit to exist, we actually need to consider the left side limit, the right side limit, and it better be equal to the same value. Otherwise, we're going to say, otherwise, what do we say? If that's not the case, so if the limit as x approaches a of f of x does not give the same value from the left and from the right, the same value from the left and from the right. What am I saying here in mathematical language? What am I saying? I'm saying that if limit as x approaches a from the left differs from the limit as x approaches a from the right. So if that's the case, if the left limit and the right limit are not equal, then we simply say that the limit does not exist. Then limit as x approaches a does not exist. And you know what? We can use the well-known high school acronym DNE for does not exist. And that's another fundamental difference between plug in a value in a function and evaluate a limit. Because you can plug a value into a function and it will actually completely exist, but the left and the right limit will not. Yeah, strange enough, huh? We're going to see examples of this coming up pretty soon. So again, a little pause before I erase this. And we're going to move on to the three types of limits. We will consider three types of limits. First type is going to be numerical. That's what we just did with the previous example. Numerical means let's use numbers to evaluate the limit. Then we're going to look at some graphical limits. And finally, we're going to look at perhaps the most practical type, algebraic limits. So numerical, graphical, and algebraic. Okay, so let's take a look at numerical limits for a quick moment. Numerical limit. What does that mean? It means that if we actually want to evaluate the limit as x approaches something, we need to do this using numbers, both from the left side or from the right side. So what we do for this, I guess, is best illustrated with an example. So let's take a look at an example here. That's going to be example 2. So evaluate numerically the limit as x approaches 1. Why don't we just stick to the example we just saw? It's going to go fast because we already have the answers. We computed them. So this really I present to you so that we simply organize our work a little better than we did before. So evaluate numerically the limit as x approaches 1 of x squared plus x. So how do we do this in an organized format? We do it in a table. So in a table, we're going to do this. We're going to have here x, and we're going to have here f of x. Okay? Now, right smack in the middle, I'm going to put the value that I am approaching. And that's going to be the value of 1. Now, I am going to approach this basically from the right and from the left with the values that you and I took a look at before. And what were these values? You remember? Well, we actually started off with something like 1.1 here. And then we went with 1.01 as we get close to 1. And this is the value that is the closest to 1, 1.001, right? And on the other side, well, here, this guy, the one that was the furthest away from 1 is 0.9. And then we had 0.99. and 0.999. So neatly organized in a table, we get something like this. Here, we're clearly going to put the values that are here into f of x, and we're going to find pretty much the same things as we found before. So if you remember, when we put in 0.9 into this, we get 1.71. This is 1.9701. This is 1.997,997,001. This here, we don't know, okay? Because a limit is not the same as evaluating a function. You can't replace x is equal to 1 into this. It goes against the definition of limit. Of course, many of you have noticed that if we do plug it in, well, we get 1 squared plus 1, we get 2, which is the value of the limit we've established before. But we can't do that for now. We're going to have special rules a little later on in this chapter. But for now, we stick to the definition. We approach from the left. We approach from the right. So 1.001, what did we get 1.001? Well, we got 2.00301. For 1.01, we got 2.0301, and this was just 2.31 here. So the idea now, it's pretty simple, is to see, okay, going from here to here, from here to here, as I'm getting closer and closer and closer to 1, what is the value that I am getting close to? Well, clearly 1.7, 1.97, 1.997, we are getting close to 2. Limit as x approaches 1 from the left is 2. We already knew that, right? We're just organizing our work a little better. So from here to here, 2.3 to 2.03, 2.03 to 2.003. Clearly, we are also getting closer to the value of 2, this time approaching 1 from the right. And once again, because those two values are the same, we can actually come to the lovely conclusion that the limit as x approaches 1, no direction, no left, no right, of the function, we can actually write what it is, or we can write f of x, same thing, same difference, equal to 2. And that is the conclusion of this problem. So that's how you would handle a numerical limit. We'll do another example later on, but in the next video, we'll mostly tackle graphical limits and perhaps maybe another example of numerical, we'll see. So I hope this was not too heavy for the first video in calculus. I wish you well. I'll see you online if you have any questions. We will Zoom together at some point. You take care. I'll see you soon. Bye.